Hello everyone, this is Roushan, and today I am going to discuss week 12 uh, session. So in this session, I will cover the lectures which is under week 12, and in this I will solve some problem related to theory of failure. So I hope everyone has already completed the lectures of this week, and most probably this is the last session of this course, and one extra session I will conduct maybe tomorrow. So I will update you in the uh, um, end of the meeting today. So let's start today's session. That is week 12. So week 12 session. Okay. So in week 12 we have the lecture based on the theory of failure. So in this we have two lecture and the lectures are theory of failure. I'm not going to discuss the whole thing. I just simply write the expression for all the theories of failure. So we have six theory of failure in the syllabus of the solid mechanics course. So I'm just writing here. So theory of failure. So first theory is maximum principal stress theory. Maximum principal stress theory. So in this theory we have maximum of lambda, that is lambda 1, is less than yield stress of the material, tensile yield stress of the material. So this is the maximum principal stress theory. Sorry. Next is maximum shear stress theory. Maximum shear stress theory. So in this theory we have lambda 1 minus lambda 3 upon 2 is less than sigma y by 2. So basically lambda 1 and lambda 2 are the maximum principal stress value. Maximum principal stress value. It can also be written in terms of yield shear stress. So this is uh, yield stress in tension. It can also be written in terms of shear yield stress in shear, which is equal to lambda 1 minus lambda 3 upon 2 is less than tau y. Okay, which is equal to T into R upon J. So this is the maximum and minimum principal stress value. Maximum and minimum principal stress value. The next theory is distortional energy theory. So distortional energy theory. So in this theory, we have write the theory in terms of distortional energy. So distortional energy is given by total energy minus volumetric energy. So distortional energy per unit volume is given by total energy minus volumetric energy, volumetric strain energy. And volumetric strain energy is given by, first of all, I will write that strain energy per unit volume. Strain energy per unit volume. So it is given by 1 by 2e sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 nu sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. Okay. So this is the strain energy per unit volume, and the volumetric strain energy is given by this relation. Volumetric strain energy is equal to 1 by 6e 1 by 6e sigma 1 plus sigma 2 plus sigma 3 times sigma 1 plus sigma 2 plus sigma 3 times 1 minus 2 nu. And therefore, using this two relation, we can obtain the distortional energy. So finally, distortional energy is given by this relation. Distortional energy is given by 1 plus nu by 3e sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 3 sigma 1. Okay. So this is the distortion energy per unit volume. We can use this relation to calculate the yield value, maximum stress value in the material. So distortion energy, if only tension is applied, suppose if only single load, that is uniaxial load is applied along one direction, so it becomes distortion energy in the case of it becomes simply 1 plus nu by 3e sigma 1 square, because the other stress value, the other principal stress value, that is sigma 2 square and sigma 3 square, will become 0. So using the tension test, we can find the value of the permissible tensile stress. So using that relation, we can find out the critical distortion energy. So critical distortion energy is given by critical distortional energy is given by 1 plus nu upon 3e into sigma y square. The y is the yield stress in tension. Okay. And using that relation, we can find the maximum permissible stress value in the material. So it is given by this relation 1 plus nu upon 3e sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 3 sigma 1 is less than equal to 1 plus nu upon 3e sigma y square. So this is the final relation that we have. We can also write in terms of yield stress in shear. Okay, just like the maximum principal stress theory. So we can also write like this. So using that, we can write in this way: 1 plus nu upon 3e sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 3 sigma 1 is less than 1 plus nu upon e tau y square. So we can use this relation if we have given the yield stress in shear. Okay, so this is the all about the theories that we already discussed in the lecture. So this is a problem solving session. So therefore, I have discussed only the formula part. That is, I only write the expressions here. So for detailed derivation, you can look up into the lectures of this week. So the next thing that is discussed in the lecture, that is the last lecture of this week, is thermoelasticity. So in that lecture, concept of thermal stress and temperature coefficient has been discussed. So I just simply write the formula here. If you have to find the value of thermal strain, then we can use one simple formula, which is given by. So now we will discussing thermoelasticity. Thermoelasticity. So the thermal stress is given by this formula, that is thermal strain. Thermal strain is given by epsilon T is given by alpha into delta T, where alpha is the thermal coefficient, that is, we can say it coefficient of thermal expansion. Coefficient of thermal expansion. And this is the change in temperature. Okay, so thermal strain is given by this relation. So the total strain is given by simply we add the value of the thermal strain. So to find the exact value of the strain, that is the exact value of the strain that is happening in the body, is given by total strain plus thermal strain. So it is given by this relation. So epsilon xx is given by 1 by E sigma xx minus nu times sigma yy plus sigma zz plus alpha times T, or we say alpha times delta T. Similarly, epsilon yy is given by 1 by E sigma yy minus nu times sigma xx plus sigma zz plus alpha times delta T. Similarly, epsilon zz is given by 1 by E sigma zz minus nu times sigma xx plus sigma yy times plus alpha times delta T. So this is the final expression that we will use in coming question that I will discuss later on in this session. So this is all about the week 12 theory part. So in this session, in this week, that is week 12, two parts have been discussed. The first part is about the theory of failure, and the second part is about thermoelasticity. So based on these two topics, I will solve some problem right now from basics to advanced question that will help you to solve the assignment problem that is already covered in the uh, solid mechanics course. So week 12, while solving the week 12 assignment question, you will be able to see the questions right now. And after going through this session, you can able to solve those questions because it is easier one than this question that I am going to solve right now. So let's start the today problem solving session, starting with the problem based on theory of failure. So the first problem is based on theory of failure. Problem 1. So I am writing the question. The problem is a cylindrical tank is made in steel is made in steel for which ultimate tensile strength is 150 megapascal, and the pressure inside the cylinder and the pressure inside the cylinder is to be 1.3 megapascal. Okay, so the question is using theory of maximum principal stress, using theories of maximum principal stress, maximum shearing stress, maximum principal stress, maximum shearing stress, and distortional energy theory. And distortional energy find the thickness of the cylinder, find the thickness of the cylinder, find the thickness of the cylinder if diameter of the cylinder is, if diameter of the cylinder is, the first part is 1.5 meter, the second is 1 meter, third is 0.5 meter. Use, sorry, it's meter. Use factor of safety. Use factor of safety is equal to 5. Okay. So we have one cylindrical tank which is made of steel, for which ultimate tensile strength is 150 megapascal, and the pressure inside the cylinder is to be 1.3 megapascal. So we have one cylindrical tank which is made of steel, which has ultimate tensile strength of equal to 150 megapascal, and the pressure, there is a pressure inside the cylinder is 1.3 megapascal. The question is, using the theory of maximum principal stress, maximum shearing stress, and distortion energy, we have to find the thickness of the cylinder. And here we have given three diameter, that is 1.5 meter. For 1.5 meter we have to calculate 1 meter, we have to calculate, and for 0.5 meter diameter we have to calculate the thickness of the cylinder. So as we know that in a cylinder of having internal pressure, we have two stress. The first one is circumferential stress, and the second one is hoop stress. So using that relation, we can simply find out the two tensile stresses. Both of these stresses are tensile in nature: the circumferential stress and the hoop stress. So starting with the solution for this question. So hoop stress is given by P into D upon 2T, where T is the thickness of the body, P is the internal pressure acting on the cylinder, D is the diameter of the cylinder. So it is given by, what is the P here? 1.3 megapascal. Diameter is D times 2 into T. And what is the longitudinal stress, or we can say circumferential stress, is given by PD upon 40. So P here is 1.3 times D upon 4 into T. Now here we can see that both the principal stress are positive. You can see here that both the principal stresses are positive. That is, sigma H and sigma L are both are positive. So therefore, maximum shear stress is given by maximum shear stress is given by lambda 1 minus lambda 3 upon 2, where lambda 3 is the minimum principal stress and lambda 1 is the maximum principal stress. Here minimum principal stress value is 0 and the maximum principal stress value is 1.3 d upon 2t. So 1.3 into d upon 2t, 2 times 2t minus 0, which is equal to 1.3 d upon 4t. Okay. Now we can see that here that the maximum shear stress theory, that is lambda 1 minus lambda 3 upon 2, and the maximum principal stress and the maximum shear stress theory, both are same here. Why it is same? Because both the stresses are in the same quadrant, that is the first quadrant, and the minimum principal stress here is 0. So we can say that here the value of thickness that is coming out to be from principal stress theory and the shear stress theory are both are same, because here they are both the stresses are in the first quadrant and the third stress, that is the minimum principal stress, is 0. So we can write in the uh, we can write here that in the first quadrant the maximum principal stress theory, in the first quadrant where sigma h and sigma l both are positive, so maximum shear stress theory and maximum principal stress theory are same. Okay, so we can say that here that longitudinal stress is equal to circumferential stress, and circumferential stress is given by ultimate tensile stress upon factor of safety, which is equal to 150 upon 3. Sorry, 5. The factor of safety is 5 mentioned there. So it is given by 30 Newton, 30 megapascal. Okay, so this is the yield stress in tension, or we say shear, because here both the theories are same, give the same result. Now we have the equation, that is 1.3 d upon 4t is given by 30 megapascal. So 1.3d, the first thing is 1.3d upon 2t and the second thing is 1.4d upon 1.3d upon 2t and 1.3d upon 4t. So using maximum shear stress, or we can use maximum principal stress, both are same here. So I am using here maximum principal stress theory. So it is given by lambda 1 is be less than sigma y. Okay. So what is the lambda 1 value here? Lambda 1 is 1.3d upon 2t. So we are getting equating with the 30 megapascal. So it becomes 1.3d upon equal to 60t, and from here t equal to 1.3d upon 60. Okay, now we have three diameter value, so we can using all the diameter values one by one. So first case is for diameter equal to 1.5 meter, which is nothing but equal to 1500 mm. So for this we have t equal to 1.3 into 1500 upon 60. 1.3 into 25. So it will become 32.5 mm. The next question is for diameter equal to 1 meter, that is 1000 mm. So for this t equal to 1.3 into 1000 upon 60. So it is given by 21 point, approximately coming out to be 21.7 mm. The next question is for diameter equal to 0.5 mm, that is 500 mm. So for diameter equal to 0.5 meter, that is 500 mm. It is given by T equal to 1.3 into 500 upon 60, which is coming out to be 10.8 mm. Okay, I hope you are understanding this question. In the meanwhile, if you have any doubt in between, I am solving the question. So you can raise your hand or you can ask in the chat box. So it will be better for you so that you can easily solve the assignment problem. So this is all about the maximum principal stress theory and the maximum shear stress theory. So here I am not calculating using the maximum shear stress theory, because here, as both the principal stresses are in the first quadrant and the minimum principal stress value is 0, so therefore the shear stress, the thickness coming from shear stress theory and principal stress theory are same. So you can use any one of them. So yes, this is all about the first part. The second part of this question is distortion energy theory, using distortion energy theory. So question using distortion energy theory. Using distortional energy, sorry, distortional energy theory. So here we have only two principal stresses. The third principal stress is 0 here. So that's why we are using the concept here, that is sigma 1 square minus sigma 1 sigma 2. If you use that relation, as I discussed earlier, if you put the value of sigma 1 square and sigma 3 square value is if the sigma 3 square value is 0, then only the that will remain in this expression is sigma 1 square plus sigma 2 square minus sigma 1 sigma 2 is less than equal to tau y square. So I am using that relation only. So sigma 1 square minus sigma 1 sigma 2 plus sigma 2 square equal to sigma c square. And here we have calculated the value of sigma c, that is 150 upon 5. We can also call it as sigma y for your clarity, because in the above expression I am using only sigma y, so that's why I'm using a sigma y value. So it is given by sigma y. So sigma 1 square is 1.3d upon 2 sigma c minus half into 1.3d upon 2 sigma y whole square plus 1.4 1.3d upon 2 sigma y whole square equal to, so what I am doing here, so I simply use that relation. Yeah, I am simply using that relation 1.3d upon 2t and 1.3d upon 4t. So 1 by 4 1.3d upon 2 sigma y, and sigma y I take sigma y value from the right hand side to the left hand side, and the value of t going from LHS to RHS. So using that, uh, what is left from the RHS is t square. So if we take common as 1.3 d upon 2 sigma y whole square, the remaining thing that I left here is 1 minus 1 by 2, and from here is it's 1 by 4 equal to 0.317 d upon 30 whole square. Okay, so it's come from here. It's come from here. Sigma c value, that is, yeah, which is equal to So it is t square. And after solving this, we can find the value of this one. That is 0.317 d upon 30 whole square equal to t square. Now we have to calculate the value of the thickness for each diameter value that is given in the question. So for diameter equal to 1.5 meter, that is 1500 mm. T1 equal to, from here we can use the relation. T1 is coming out to be 28.15 mm. For D equal to 1 meter, that is 1000 mm. T1 is coming out to be 18.77 mm. And for D equal to 0.5 meter, that is 500 mm. T1 is coming out to be 9.40 mm. So this is the final value of the diameter, final value of the thickness that is coming from this relation. Okay, so this is the final answer for this question. In this question, we have three questions. That is, we have to find the value of thickness using maximum shear stress theory, maximum principal stress theory, and distortion energy theories. Because here sigma 1 and sigma 3 are in the same quadrant and sigma 3 value is 0. Therefore, we can say that maximum shear stress theory and maximum principal stress theory yield the same value of thickness. However, using distortion energy theory, we find the value of the thickness for each of the diameter value which is given in the question. So this is all about the first question. Now we can move to the second question, which is again based on the theory of failure. And this is a very good question. So you can please give attention here. So the second question is, that is problem 2. This problem is a circular shaft, a solid circular shaft is subjected to a solid circular shaft is subjected to a bending moment of 3 kilonewton meter and a torque of 1 kilonewton meter. The shaft is to be made in the shaft is to be made in the shaft is to be made in carbon steel for which sigma y equal to 480 megapascal and tau y equal to 265 megapascal. Okay, and the question is, if the beginning of plastic deformation is to be avoided, if the beginning of plastic deformation is to be avoided, calculate the shaft diameter. Calculate the shaft diameter using maximum principal stress theory, maximum shear stress theory, and distortion energy theory. The first part of this question is using maximum principal stress theory, maximum principal stress theory, maximum shear stress theory, and distortional energy theory. And distortion energy theory. Okay. So we have this shaft. and here is a bending moment applied, that is M, and here is one torque is also applied, that is M T. From here also torque is applied. M T. This is the center of the shaft. D is the diameter of the shaft. I'm repeating the question. The question is, a solid circular shaft is subjected to a bending moment of 3 kilonewton meter and a torque of 1 kilonewton meter. The shaft is to be made in carbon steel for which sigma y equal to 480, that is yield stress and tension is 480 megapascal and yield stress and shear is 265 megapascal. The question is, if the beginning of the plastic deformation is to be avoided, calculate the shaft diameter using maximum principal stress theory, maximum shear stress theory, and distortion energy theory. So here we have to use three different theory, and we have to find the value of the maximum uh, diameter of the shaft so that it can withstand all the maximum stress till the failure. That is, here it is mentioned that till the beginning of plastic deformation, that means till the failure of the material, because it is a ductile material. Here it is mentioned also that it's a carbon steel, so it's ductile. So let's start with the solution of all this problem. So first we have to find out the equivalent bending moment and the equivalent twisting moment. So equivalent bending moment, we can use that relation, equivalent bending moment. Equivalent bending moment, we have to calculate equivalent bending moment, which is given by 1 by 2 m, that is bending moment, plus under root of m square plus mt square, or half of m minus under root of m square plus mt square. Okay. So this is the value of equivalent bending moment. So it is given by 1 by 2, 3 plus root over 9 plus 1, or half of 3 minus root over 9 plus 1. Because m is given as, the value of m is given as, bending moment is given as 1 kilonewton meter, 3 kilonewton meter, and mt is given as 1 kilonewton meter. So finally it coming out to be 304 kilonewton meter, or minus 0.04 kilonewton meter. So using the equivalent bending moment, we can find out the value of the maximum shear stress, which is given by sigma 1 equal to my upon I. And what is y here? D by 2, and I is pi d to the power 4 upon 64. It coming to be 32 m equivalent upon pi d to the power 4, d to the power 3, because 1 d cancel out. So 32 into m equivalent bending moment is 3.04 into 10 to the power 3 upon pi d cube, that is equal to 31 into 10 to the power cube into upon d cube. The next principal stress is given by the second equivalent bending moment, that is minus 32 into me. What is me here? So 0.04 into 10 to the power 3 upon pi d to the cube. So it comes out to be 0.41 minus 0.41 into 10 to the power 3 upon d cube Newton per meter square. So this is the value of final principal stress that is coming from the equivalent bending moment. Now we have to find the value of the equivalent torque. So equivalent torque. So it is given by equivalent torque is given by under root of m square plus mt square, which is equal to 9 plus 1, that is root 10, which is equal to approximately 3.08 into 10 to the power 3 Newton meter. So from here we can find the value of the maximum shear stress. So tau max is given by 16 m equivalent torque upon pi d cube, which is equal to 16 into 3.08 into 10 to the power cube upon pi d cube. So the value of this is given by so the value of this is given by if I calculate this, finally I get it equal to, it will become 15.7 upon d cube into 10 to the power 3 Newton per meter square. Okay. Now we have to use here two different theories. The first one is maximum shear stress theory, and the second one is maximum principal stress theory. So we're first using maximum principal stress theory. Maximum principal stress theory. That is sigma 1 equal to sigma y here. That is sigma 1 is given by 31 10 to the power 3 upon d cube equal to sigma y, and sigma y value is given as 480 megapascal, but it's in Newton per mm square and it's Newton per meter square. So we have to subtract it with power 10 to the power minus 9 equal to 480. So from here we can find the value of d, which is coming out to be 40.12 mm. So the final radius that is coming out from the maximum principal stress theory is 40.12 mm. Now using the maximum shearing stress theory, maximum shearing stress theory. maximum shearing stress theory. So with this theory, we have tau max equal to tau y, which is equal to 15.7 into 10 to the power 3 upon d cube into 10 to the power minus 9, because we have to convert it in Newton per meter square from both the sides, 265. So from here, d is coming out to be, we have to calculate this. So anyone please tell the answer. Okay, so sorry for the delay, I think. Mm, so here I am. Yeah, so value of this radius is coming out to be 39 mm. If you calculate this, it is coming out to be 39 mm. Now we have to also use the third part of this question, that is we have to use the distortional energy theory. Distortional energy theory. Okay, so it is given by distortional energy theory. So distortional energy theory, using distortional energy theory, we have the expression sigma 1 square minus sigma 1 sigma 2 plus sigma 2 square is equal to sigma y whole square. So using the expression of sigma 1, sigma 2 and sigma y, we can write here 31, sigma 1 is 31, 10 to the power 6 upon d cube whole square minus sigma 1, sigma 2 is 31 into 0.41 into d 10 to the power 12. If you see from here that sigma 1 value, so sigma 1 is 31, 10 to the power 6, that is 12, 9 or 3, 12 upon d cube. So that is the value of sigma 1 and sigma 2 upon d cube whole square plus 0.4 into 10 to the power 6 upon d cube whole square equal to 480 whole square. So the final expression, if I solve this numerics, so we will get 10 to the power 6 upon d cube whole square minus 961 minus 12.71. It is coming out to be, if you calculate this, it will coming out to be 12.71 plus 0.106 equal to equal to 30.8 into 10 to the power 6 upon d cube whole square, which is coming out to be 480 whole square. So from here, if we calculate the value of d, it is coming out to be 40 mm. Okay. So the final expression that is coming out using the distortion energy theory is 40 mm. Okay. So this is all about the question number, problem number 2. Now move on to the problem number 3, which is again based on the theory of failure. So problem number 3. Let's start problem number 3. Problem 3. So the third problem is a wall bracket. This is a very good question. So I please give the attention here because it's a very good question and a difficult one of the most difficult question of the theory of failure, and it will clear all your concepts regarding the theory of failure questions, how you can solve it. Using this question, we can split actually in the multiple choice question. There will be a question which is somewhere a part of this question, some part of this question. So it's a very big question, and in the assignment or in the final proctored exam, you will ask some part of this question maybe. So please give attention to this question because it's a very important question for theory of failure. So the question is a wall bracket with a rectangular cross section, a wall bracket with a rectangular cross section, a wall bracket with a rectangular cross section is shown in figure is shown in figure. Okay. The depth of the cross section, the depth of the cross section, the depth of the cross section is twice of its width, is twice of its width. Okay. The force P acting on the bracket, the force P is acting on the bracket, the force P is acting on the bracket at 60° to the vertical is 5 kilonewton. The material of the bracket is gray cast iron. The material is made up of gray cast iron. The material of the bracket is the material of the bracket is gray cast iron of yield stress 200 gigapascal, of yield stress 200 megapascal. Okay. And the factor of safety is and the factor of safety is and the factor of safety is 3.5. Determine the dimensions of the cross section. Determine the dimension of the cross section. Determine the dimensions of the cross section of the bracket. Assume maximum normal stress theory of failure. So here it's also mentioned that what theory we have to use. So assuming maximum normal stress theory of failure. Stress theory of failure. So I'm repeating the question. A wall bracket with a rectangular cross section is shown in the figure. So I'm draw the figure first. So the figure is Here there is a load is acting. A load is acting P. This length is, so this is a center. This length is 150 mm. This is a section of thickness 2T. This thickness is T. This point is A. This is X section. This length is 300. Okay. This angle is 60 degree. So yeah, so this is a wall bracket. The depth of the cross section is twice of its width. That is, the depth is twice of its width. So if the width is T, so the depth of the cross section is 2T. The force P is acting on the bracket at 60 degree. You can see here a force P is acting here, which is at 60 degree from the vertical, is 5 kilonewton. It's given in the question that it is equal to 5 kilonewton. The material of the bracket is gray cast iron of yield stress 200 megapascal. The yield stress of this material is 200 megapascal, and the factor of safety is taken is 3.5. Determine the dimension of the cross section of the bracket. So we have to find the width and the thickness of the bracket. Here we have to assume the maximum normal stress theory of failure. So this is a bracket. So we can simply write the given values here. So we have first given the value of load, that is P, which is equal to 5 kilonewton. The second thing that we have mentioned is SY, that is the yield stress, that is 200 megapascal. Next is factor of safety, which is given as 3.5. And next is depth upon width ratio, which is given as 2. So this is the given values in the problem. So first we have to find the permissible stress. Okay, so permissible stress value. Permissible stress value. Permissible stress, that is sigma y. So permissible stress is given by sigma max, which is given by Sy upon factor of safety, which is 200 upon 3.5, which is somewhere approximately equal to 57.14 Newton per mm square. So this is the value of permissible stress. Now we have to calculate, because you can see that our load P is acting at an angle of 60 degrees from the vertical. So we have to calculate the bending and tensile stress, direct bending and tensile stresses. Okay. So first we break the component of P, break the P into two components, the horizontal and the vertical component. So vertical component will become P cos 30, P cos 60. And the horizontal component will become P sin 60. Okay. So let's start with the horizontal component. So horizontal component is become PH. So we can write a name here, PH and PV. Horizontal load component and the vertical load component. So horizontal component PH equal to P sin 60. P sin 60, which is equal to 5000 sin 60. And sin 60 is 1 root 3 by 2. If we calculate this, it's coming out to be 4330.13 Newton. Next is vertical component. Vertical component is PV, which is equal to P cos 60. Cos 60 is 1 by 2. That is, it's coming out to be 2500 Newton. Now, the bending moment at this section. If you want to find the bending moment at this section, so it will create a bending moment of P cos 60. P cos 60 multiplied by this distance, that is 300, and it will create a bending moment of P sin 60 multiplied by this distance, that is 150. So bending moment at the section XX is given by, that is bending moment, sorry, bending moment at the section XX is given by MB equal to, so first we have to find the using this, that is PV. So PV multiplied by perpendicular distance from the section, so it's equal to 300. So P cos 60 into 300. So PV into 300 plus PH into 150. So it's coming out to be PV. We already find the value of PV, that is 2500 into 300 plus 4330.13 into 150. So finally, the value that is coming from the calculation is 1399.52 into 10 to the power 3 Newton meter mm, because the distance is in mm. So it's 300 mm and it's also in 150 mm. So the bending moment about section XX is given by 1399.52 Newton mm into 10 to the power 3. Now we have to find the question. The question is asking for the dimension. So for dimension, we have to find the value of permissible stress. So for this, we have found the value of bending moment, and then we find the value of permissible stress. So sigma b, that is bending stress first, is given by mv. Okay. So sigma b, that is bending stress, is given by mb y upon I. mb y upon y. mb y upon I. So it's given by, MB is given by 1399.52. Y is the distance into 10 to the power 3. Y is the distance of this moment, that is vertical moment. So what is Y here? So you can see the distance of the cross section from the mid plane from the centroid is T. So it becomes T, and I is given by BH cube upon 12. So it is given by B is T here because width is T, thickness is 2T, 2T cube into 12. Now after calculating this, we get the value of this one, 2099.28 into 10 to the power 3 upon T cube Newton per mm square. So this is the final value that is coming out to be. Now here we can see that this, due to this load P, we have two bending moment occur. The vertical component uh, yields a bending moment about this axis. So it's given by P cos 30 into 150 mm. 300 mm, and the horizontal component also yields a bending moment about x-axis. Here you can see that the horizontal component of this force, that is PH, creates a tensile stress in this section, and the vertical force PV creates a shear stress in this section. So we also have to find the permissible stress due to stretching and permissible stress due to shearing. Let's do this. So direct tensile stress, direct tensile stress due to component pH is given by direct tensile stress due to component pH is given by sigma T, which is equal to pH upon A. What is the horizontal component? pH is given by, we already calculated that. So pH is given by 4330.13. 4330.13 upon area. Area is width into thickness, that is T into 2T. That is 2T square. So it's given by 2165.07 upon T square Newton per mm square. So it's the direct tensile stress. Now the vertical component, that is PV, induces shear stress at this section XX. So we also have to calculate that shear stress. But for now, we have neglected that shear part because we have to use the maximum normal stress theory. So we have neglected that shear part, that is the shear stress due to PV, that is vertical load, vertical component of load P. So we have neglected shear because it is very small. Now we have to calculate the value of maximum stress, that is the total stress. So using maximum principal stress theory, we have total stress is equal to, or we say less than permissible stress, that is sigma max. It is given by sigma B plus sigma T, which is now equal to sigma max, to find out the value of the thickness and the width. By 2099, 2099.28, 2099.28 into 10 to the power 3 upon T cube plus 2165.07 upon T square. It's T square. Yeah. Sigma T is given by T square is equal to sigma max, which is already obtained above, which is equal to 57.14. 57.14. So after solving this, we come out to a quadratic equation in terms of T. So it is given by T cube. It's a cubic equation, sorry. T cube minus 37.89 T minus 36739.24 equal to 0. Okay, if we solve this, we finally come out to a value. So we can solve this cubic equation. You can really get the value of T, that is the uh, thickness of the bracket. Okay, so you can solve this equation using calculator, using scientific calculator. You can solve this question. So I am solving this equation using calculator. So let's solve this. So cubic equation. So it's 1 minus 30. Six, seven. So we have three solutions. The only solution that is a real number and not negative, of course, is t equal to 33.62. So this is the value of the thickness. So width is given by, so thickness value is t. So we have already find the value of t, which is 33.62 mm. So this is all about this question. In this question, we have to find the dimension of the cross section. So we already find the value of t. So we can get the value of thickness by multiplying the value of t by 2, and t is already the width of the strip, width of the bracket. So in this question, what we have done is we simply start from the basics. That is, we have to calculate the permissible stress. For that, we need the moment and the permissible tensile stress, which is already acting in the bracket. So here we have a load which is inclined at angle 60 degree from the vertical, and due to this load, we have two bending moment due to horizontal component and bending moment due to vertical component. We have found the bending moment due to these two load component. Then we have one tensile stress component due to this horizontal component force at the section XX. We also have shear component, but we have neglected the shear stress because it's a very small value. So we have neglected that part. And after that, we find the value of bending stress and the tensile stress. And we have compared it with the maximum stress using the maximum principal stress theory, and using the relation, we come out to be a cubic equation in terms of T. And using the any calculator, scientific calculator, we find the roots of this equation, which is coming out to be a positive root, that is coming out to be a 33.62 mm. So this is the final answer for this question. Now move on to the next question, which is also a very good question. Of course, this is also a very complicated and a very general question of a shaft. So I'm writing this question. That is problem number 4. Problem 4. So the question is, the shaft of an overhang overhang crank subjected to a force P of 1 kilonewton is shown in figure. The shaft is made of plain carbon steel. The shaft is made of plain carbon steel and the tensile yield strength and the tensile yield strength is 380 Newton per mm square. Okay. Here the factor of safety is to be taken as 2. The factor of safety is 2. And the question is, determine the diameter of the shaft using maximum shear stress theory. Determine the diameter of the shaft using the maximum shear stress theory. Using the maximum shear stress theory. Okay, so I'm drawing the figure, so you can draw with me. This is the axis we have in this figure. So this is y-axis, this is z-axis, and this is the center is along x-axis. Okay, now we have the length. So here a load is applied. So first I am drawing the center. So this distance is, let me draw with other color. So this distance is, this distance is 250. Okay. Then here a load P is applied, which is at a distance of 500 from this one. And yeah, so this is all about the question. This is point A, this is point Z, this is point B already. Yeah, so this is the question we have. I'm coming to the solution part. The shaft I'm repeating the question one more time. The shaft of an overhang crank subjected to a force P of 1 kilonewton is shown in figure. So here we have a figure shown. You can see a shaft here, which is made up of plain carbon steel, and the tensile strength is 380 Newton per meter square. So tensile strength is 380 Newton per mm square. The factor of safety is to be taken here is 2. So the question is determine the diameter of the shaft using maximum shear stress theory. So we have to find the uh, diameter of the shaft using maximum shear stress theory. So let's begin this problem. So here we have given load which is equal to P equal to 1 kilonewton. So given here that P equal to 1 kilonewton, SYT that is in tension is given as 380 Newton per mm square. It's already mentioned in the question. Now we have to find the permissible shear stress. So permissible shear stress. Okay. So permissible shear stress is given by S X Y, which is given by S Y S. Permissible shear stress is given by 0.5 of SYT, which is given by 0.5 of 380, which is equal to 190 Newton per mm square. Okay. So this is the permissible shear stress. So permissible shear stress is given by this equation. So the permissible shear stress is tau max equal to S y s upon factor of safety. So here factor of safety is given as 2. So it becomes 190 upon 2, which is equal to 95 Newton per mm square. Now we have to calculate to find out the diameter of the shaft, we have to calculate the torsion and bending shear stress acting about this point. So first we have to calculate torsion and bending shear stress. For that we have to calculate the bending and torsion moment, that is torque. So bending moment about this one, that is this point. So this distance is this distance is 500, and this distance is 400, 250. So moment is given by because here it becomes bending, because you can see here from it will create bending about A. The load P creates bending about A, point A. So the distance here is 250. That's why it is given by moment about P is given by P into 250, which is equal to 1000 into 250, which is equal to 250 into 10 to the power 3 Newton mm. Next is torque is given by P into 500, which is equal to 1000 into 500, which is equal to 500 into 10 to the power 3 Newton mm. Now we have to calculate the bending stress. Sigma B is equal to mvy upon I. And we already calculated the value of mv, which is equal to 250 into 10 to the power 3 into d by 2. Why is d by 2? Because the distance from the centroid to the topmost is d by 2, because the total diameter of the cross section is d. Pi d to the power 4 upon 64. So after putting the value and calculating this expression, we finally get 2546.48 into 10 to the power 3 upon d cube, Newton per mm to the power 4, sorry, square, Newton per mm square. Now coming to the torque, that is the shear stress, is given by m into r upon j, mt into r upon j. So it is given by 500 into 10 to the power 3 into d by 2 upon pi d to the power 4 upon 32, which is equal to 2546 upon 48 into 10 to the power 3 upon d cube, Newton per mm square. So this is the value of shear stress. Now we have to calculate the maximum shear stress. So maximum shear stress is because we have to use here maximum shear stress theory. So we have to find the value of maximum shear stress. So maximum shear stress we can find out using Mohr circle. So maximum shear stress is given by using Mohr circle. We can find out the maximum shear stress because here we have the bending stress and the shear stress. So using Mohr circle, we can find out the value of maximum shear stress. So sigma x upon 2 whole square plus tau x z whole square. Now here you can see from the figure that at point A corresponding Mohr circle is shown in figure 4.4. So from here we can draw the figure of the Mohr circle, how it looks. So we have one cross section, we have one plane of stress, and here we have acting a tensile stress sigma x, and we have shear stress acting tau zx, tau xz, similarly tau zx, tau xz. At point A, sigma x equal to sigma x equal to sigma b. So sigma x equal to sigma b, which is equal to 2546.48 into 10 to the power 3 upon d cube. Similarly, tau equal to tau xz equal to tau zx, which is equal to 2546.48 into 10 to the power 3 upon d cube. So both of these are in Newton per mm square. Now using the Mohr circle, so tau max equal to root over tau max equal to root over 2546.48 upon 2d cube whole square plus 2.2546.48 upon d cube whole square. So it is coming into 10 to the power 3. So it is coming out to be 2847.05 into 10 to the power 3 upon d cube. Okay. So this is the final expression of the maximum shear stress value. Now it's already mentioned in the question that ultimate, it's mentioned in the question that uh, SYT, that is the yield stressing tension, is given the question is 380 Newton per mm square, and here we have to use the maximum shear stress theory. So we have already find the value of permissible shear stress, that is SYS, which is equal to 190 Newton per mm square. Now using this concept, we can now find out the value of shaft diameter using maximum shear stress theory. We have tau max equal to 95, that is 2847.05 into 10 to the power cube upon d cube. Okay. It finally comes out to be d is equal to 40, sorry, not 40, d coming out to be 31.06 mm. So this is the final answer that we have for this question. So in this question, we have already asked that we have the question based on the uh, theory of failure. Okay. So today we have solved 4 problems based on the theory of failure. So all these 4 questions are very good question based on the theory of failure. And today I will not solve the problem based on thermoelasticity. So therefore I will take one more session in which I will solve some problem based on thermoelasticity, and one or two more question based on the overall course structure that I will solve basically problem based on bending and twisting of beams. So I will take the session tomorrow at the same time, that is from 6 p.m. to 8 p.m. So stay tuned, and tomorrow will be the last session for this course. And thank you for joining today's session. It will very grateful to me that I will take the sessions for you. And if you have any doubt after the session, you can please get in touch with me. You can also write in the chat box where in the YouTube channel of mine, where I have posted all the recorded live sessions. of this 12-week course. So thank you again for joining today, and let's meet tomorrow again, which is the last session for this course. Thank you. Now you can leave the meeting now.